Okay, how about now? Yeah, I can hear it. Okay, great. Okay, yeah, good afternoon. Hopefully you guys are not too tired after a very long day full of talks. And I have to say, for myself, I learned a lot over the last 2 days, in particular also in the many side conversations that emerged, and very much wanted to thank the organizers for putting this together. In this talk, I wanted to present recent work, or it's also partially, to a good degree, a review of work we have been doing in the area of machine learning, taking advantage of quantum computation, in particular adiabatic quantum computation. And the real hard work is done by Vasil Denchev, who is doing his PhD at Purdue on this topic. Then, of course, we get a lot of help from the D-Wave team, Bill McGrady and his crew, helping with the hardware side of things. And myself, I work at Google, and my day job there is developing visual search services. So I want to start out with a quote of one of my intellectual heroes, David Deutsch, who is also one of the fathers of quantum computing. And I'm not sure who had a chance to read his recent book, The Beginning of Infinity, which I think talks a lot to a person like myself who works in AI, machine learning. He's saying that I argue that all progress, both theoretical and practical, has resulted from a single human activity, the quest for what I call good explanations. And I think I, for one, would agree with this, and I think many of us would. And the reason I put this up here is to make the point that not all applications of quantum computation are born alike. There are more important ones and less important ones, or you get more internal investment on some than others. And if we could, essentially AI is the project of mechanizing this, to come up with good explanations by machines, to automatize this. And sometimes when I look at areas of physics, let's say you look at the standard model on a couple of pages, and you see there are various mathematical structures being used to ultimately fit to observed data, then you see, and from a machine learning perspective, this sort of calls for being automatized at some point. Because today there are only very few humans left who really can handle the most advanced theories in physics. Let's say if you go to string theory, same thing. You know, there are various constructs that you can use. It's probably not sure that they're unique. You could mix and match them in different ways to construct the theory, but only very few humans are still capable of holding this in their head. And even those humans are already relying on machines. So I think it's reasonable to call or to argue that a good investment is to make this quest for good explanations, to automatize it and see what quantum computing can do in this area. And then another quote, David Deutsch thinks that the field of artificial intelligence has made no progress because there is an unresolved philosophical problem at its heart. We do not understand how creativity works. Now, I'm not quite as sure about this statement as I was about the first one. I think we have at least some notions of how to model creativity. Actually, we had a few years ago Murray Gell-Mann, the Nobel Prize winner at Google, giving a talk on creativity. And you might get a kick out of it. He essentially drew an objective function, and then he pointed to a steep global minimum, and he said, finding this steep global minimum, that is actually a good model for what creativity does. And indeed, in everyday language, if there's something like a constraint satisfaction problem that we don't call it that in everyday language, but that is often what, let's say, in architect or engineer has to solve, and if he comes up with a good solution, we call this creative. So what I want to argue, we can debate whether our models of creativity are already sufficient or not, but from these short descriptions, I think we have a strong indication that quantum processes will play a role in making whatever we think is a good model for a creative process, make this creative process work even better. So I think deriving from this, I would argue that we will find that quantum AI is the most creative process allowed under the known laws of physics, at least to the level, let's say, I know that at Caltech they're already looking at the additional computational resources that may ensue from quantum gravity going beyond just standard quantum mechanics, but not going into these exotic territories. Employing quantum processes in this program, I think, is a valuable thing to do. So coming down to earth, and let's see sort of first concrete steps how we can employ quantum mechanics to do AI better. And we are looking here at sort of the most simple thing, or sort of our benchmark, is training a binary classifier, which is, of course, a far cry from what I alluded to earlier, to automatize physical theory building. But that's sort of, in a way, contains already the important ingredients. That is, we have some observations of the world, here marked in some feature space as the blue guys and the red guys. And forming a binary classification is essentially classifying the world in, okay, I call the blue guys the good ones and the red ones the bad ones, so I label those with +1, those with -1. So that is a simple, probably the simplest possible way of modeling the world. You see it just in black and white. And how is this done? So to do a binary classifier, you have a function, h of x, and this function is parameterized with a set of parameters which are typically referred to as weights. This comes from synaptic weights, from sort of older neural network theory. And then the output of this function, hw of x, is y, and y, and it's a binary classifier, it is -1 or +1, the blue or the red guys. And so the task is you can change this function by essentially fiddling with the parameters w, those knobs. And what you do in training is the following. You want to find a function h that does a good job, obviously, in classifying. But classifying what? Classifying data that is given to you as training examples. Let's say earlier we heard this nice application of machine learning to find organic molecules for better, more efficient solar cells. So for 200 molecules, they knew how they perform. So they could say these are good or bad ones. So you have a training set here in my notation of size S. And then in training you do two things. Modern machine learning formulates training as an optimization problem, which has two terms you try to minimize. And the first one is referred to as the loss function, which essentially measures how many times do I make an error on my training set and how many times do I get it right. So that's reasonable that you want to be as good as possible on your training set. But that alone is not good enough. You need a second term that is referred to as regularization, and that essentially controls the complexity of the classifier. Now, earlier in the David Deutsch statement, he said what I call good explanations. And in his book, he essentially said, so what is a good explanation versus a bad explanation? He argues a good explanation is one that I can not vary much, that any piece I take out of the explanation, then the explanation breaks down, versus an explanation that has a lot of extraneous features that I could take off and still make the same predictions. Machine learning has formalized that to a good degree, and I know people here are not necessarily too familiar with machine learning. I think here's an easy way to understand what the regularization does. Let's assume here, this example from Bishop, you have data that is drawn from essentially a sinus process. So you have these little dots there, which are the, actually I'll get a pointer. So that's your training data, and you try, you try to fit a function to it. So if your model is too primitive, let's say you just tried, here the model is actually a polynomial. If your polynomial is just of order 0, constant, you will not do a very good job of explaining your data. So as you increase the degree of your polynomial, you can explain the data better and better. But you're not doing yourself a favor increasing it by too much. Here you see if m equals 9, then you get, in this toy example, all training examples correct. But you can see that the prediction for new unseen data will be very poor. And that's very important to keep in mind. In machine learning, you use your training set to train up, define your classifier, is defining your W. But what you're really after is not good training error, meaning a low training error, is a necessary condition for having a good classifier, but it doesn't guarantee yet that you will do well on new unseen data, but that's what you're after. That's called a generalization error. We want to be good on new examples that we haven't seen before in the training set. And that's why you need this regularization parameter. Typically, the simplest explanation is the best one. And the regularization just ensures that you keep your model simple. And so a good explanation, simple explanation. Again, training is optimization over those two terms, loss and regularization. And of course, for not surprising reasons, the field of machine learning typically chooses those two functions to be convex so that you can do efficient training. But that comes as a cost. If you, because the most natural choices turn out to be non-convex. And what we will see in the slides to follow is that, first of all, if you use a convex measure for your training error, you will be not as robust to incorrectly labeled training examples. And that is always the case. If you work with large data sets that have been gleaned semi-automatically or even with manual labor, there's always incorrect examples in there. Second, if you use a regularization term that is convex, your solutions will not be as sparse. They will not be as simple and as compact as they could be. Then there's the newer theoretical work that shows that your generalization bounds, again, that's what you're after, the generalization error, the error on new unseen data. And that can be lower when you use non-convex losses. And finally, there is an inconsistency you're sitting on when you use convex objectives. That is the minimum of the objective function. Once you, assuming you can find it, it does not necessarily correspond to the minimal training error. And that means you're doing something wrong. That means if I give you a better optimizer, your classifier is not necessarily getting better. And then that means your objective is not quite right. And that actually has, to me, become sort of the litmus test when I talk to machine learning colleagues, is if I were to give you a golden solver that does a perfect job on the optimization problems that arise in your context, will you be better, or will your system be better or worse? Or can you even answer? And it often turns out that it's not clear. So that needs to be cleaned up. So emboldened by emerging quantum hardware, we went ahead and studied non-convex versions of loss and regularization, which renders the training problem formally NP-hard. And moreover, we treated it as an integer program working with weights of low bit depths. So this, I think I do not have to explain. Eddie in his initial talk, but then various others touched upon the basic principle of adiabatic quantum optimization, and that is, of course, the form of quantum computation we want to map to. So we'll just skip this slide. And the specific implementation of adiabatic quantum computation that we work with is obviously the one from D-Wave, which essentially implements the icing model in hardware. We have already heard about this earlier today, yesterday, and which is essentially computer scientists could think of this machine as a coprocessor that solves a weighted max 2-set system. And the nice thing about it is that beyond this being available today, it is the simplest many-body system. So I could imagine whether, let's say, of course I hope everything works out great, but whether in, let's say, 30, 40 years, let's say D-Wave or whatever company then is around, let's say whether the D-Wave machine per se still exists or we use other architectures then, doesn't render this type of work obsolete, because I think even if we go down to, let's say, from more macroscopic qubit implementations to truly microscopic ones, it is pretty likely in my mind that the first systems to follow D-Wave will probably still be in this range, or many of them will be in this general realm of many-body systems where you have pairwise interactions between the units, because that's just the simplest you can build. So here, this is probably in this. Oops. How do I see? Something that's a little video I wanted to show you guys. So, I don't know. Okay, sorry. It was a little illustration. Yeah, it's actually a good idea. Just go there. Okay. No, sorry for this, but I think you guys know enough about how the D-Wave chip works so that you, there was just a little cute video that illustrates it. So to go one level deeper in detail, so we talked about how a binary classifier is set up, and here we look at a specific one, which is a linear binary classifier, where we construct the classifying function h of x as the sign of a linear combination of what is often referred to as weak classifiers or feature detectors, is the HIs, and you have a global threshold B. And here, again, the idea is to find the appropriate set W so that you minimize loss and regularization. And I should maybe say here, in the different pieces of work, we have sometimes used weak classifiers, sometimes we haven't. And sometimes we use different normalizations for the W, so please don't let this throw you off. If you look too close to the details, I would have to tell you with what is the scaling and whether the H's have been used or not, but I didn't want to bring all this detail. So the main architectural elements don't depend on this. So this is the overall structure of the binary classifier we use. And this is an element I will skip over. You can find the details on the archive. The important point is, of course, that the D-Wave architecture is good for discrete optimization. And traditionally, when you do machine learning, the weights are continuous variables. So you have first order of business is to transfer or to essentially make the weights discrete. And of course, you can always do this by some binary expansion. You use IEEE 64-bit notation, let's say, for a float. But of course, if you just do it like this, you run out of qubits very quickly. And the current machine we work with is 106 qubits, so you don't want to spend 64 qubits just on a single weight. So the question had to be addressed, how many weights do we really need? And that was one of the pleasant early findings in this endeavor, that it turns out that you can get away with very few bits, often just a single bit. And that this is often beneficial in the sense that if you would have taken more bits, the generalization error gets worse. Again, I will skip over the basic, some basic arguments why that make plausible why this is true. For now, just take it as an experimental fact that often just a single, 2, 3, I think the biggest number of bits we needed for any problem was 5 bits. So that was a nice finding early on in this endeavor. So we had two different setups. One is we did training with convex loss and non-convex regularization, and then we do training with non-convex loss and convex, but convex regularization. And of course, the final piece would combine those two. So the first setup we had was we used square loss, so essentially measuring the square error the classifier does. And we have zero norm regularizations. That means the zero norm just checks how many of elements of your weight vector are non-zero. And the nice thing about this setup is that you only need of the order n qubits to represent your weights threshold. So if n is the number of weak classifiers you use in your strong classifier. So that's a nice, efficient use of the qubits. And that allows two more things to happen. This was addressed earlier by Sergio. Because this is an efficient use of qubits, you can do two things. If, for example, the first round of optimization yields a classifier of that nature where you only have T classifiers are switched on and the other W's are put to zero, which of course the zero norm regularization encourages, then you can do another round. You can iterate it. If, let's say, you have Q qubits and Q is larger than T as the number of weak classifiers already picked, then you can rerun it, and essentially the remaining Q minus T weak classifiers you can fill up with new ones that the system hasn't considered yet. And how do you pick those? Typically you do this by a boosting strategy. You say, okay, the classifier I obtained so far, I apply it to my training set, and I look which training examples do I get right already, and which ones do I still get wrong. And then I weigh those up, say pay more attention to those that are still getting wrong, so I bring up the weight of those training examples, and the ones I get right already, I weigh down, and then I pick new weak classifiers that do well on this reweighted training set. And those that do best, I will add to this optimization. So I can do this a few rounds and let the system continuously keep picking the best ones. And of course, the old optimization, or the old best solution, assuming the optimization would work perfectly, would always still be available. So the system would never get worse. It would only get better by considering better feature vectors. So that's a nice attribute. The other thing is, was also mentioned earlier already, if you needed, for some reason, a really large classifier, should say that, let's say, a couple hundred, sort of in the number that the D-Wave is reaching right now, a linear classifier with a couple hundred weak classifiers, that's already pretty big. You can do many things with a classifier of that size. But if you needed something larger, no problem. You can essentially concatenate things by taking, okay, the first strong classifier I have obtained, but I still want to make it larger, then, okay, you just freeze whatever you had so far, and you add a new section, and this way, what's this, a timer? 5 more minutes. And you can concatenate this way. So this way, you have a system that can do practical things. And but there's one thing is that it isn't good with, and that is addressed in our newer work. It doesn't deal well with outliers. So imagine you have a few examples that have been mislabeled, common occurrence. Then what would happen if you do take a convex loss, like the square loss, essentially it gets pulled over to try to make these outlier examples less bad. It's like a professor being distracted by his worst students to bring those up a little bit. He's neglecting some of his other duties. And the way you can see this here is convex losses are unbounded if I should explain what the margin is. The margin is essentially, let's go one back, how far away you are from the separating hyperplane. And if it's positive, you have a correctly classified example. If it's negative, then it's incorrectly labeled. So if you have a non-convex, a convex loss, it's not bounded. So examples that are bad cause a large penalty and cause the optimization to pay a lot of attention there. So that is why you eventually need to cap it here and say, okay, if there's a danger of some examples being wrong, you only want to cap it at a finite penalty. So that is essentially what in the newer work we have done. We introduced auxiliary variables to essentially work with a loss function that looks like this. We dubbed Q loss, and why it has this peculiar shape is essentially we wanted to cap it, but we also want to be able to implement it on the D-Wave hardware with as few auxiliary qubits as necessary. Okay, so that's the newer work, which is, it has a non-convex loss, this shape, but a convex regularization, we take L2 norm regularization. Okay, these are the two systems we set up. Then quickly some look at results we obtained. So this is earlier work, 2009, on synthetic data and on natural data. We found like a nice improvement in error rates over sort of a standard AdaBoost system. And we also found that because you add chunks of classifiers in each training round, is that you often get away with less loops than you would with less training rounds. Here the reweightings essentially count how many times do I have to reweigh my training data in the boosting sense, as I explained earlier. And you see you get away with much less loops in this global optimization strategy than with the traditional AdaBoost. So what you get is you get better error, you get more compact classifiers, you have less weak classifiers. See here, if you compare those numbers, and you get faster training. So you win essentially on all three accounts. And I'm out of time. I wanted to, there's also some guarantee why this has to work better, so it doesn't come as a surprise, because basically by what we discussed earlier, if you keep your classifier simpler, more compact, it will generalize better. You know, so what are good explanations? Essentially, Vapnik-Chemnovenkis theory formalizes this, and it will show that the more compact classifiers, if they do the same on the training side, will generalize better. The generalization errors bounds are lower. We also used this setup to do proof of concept demonstration, car detector, but I'm happy to see that other applications in the making. So this was with the still with the convex loss. With the non-convex loss, we are looking at 8 data sets that we have where we have applied it, and we found like really nice gains or robustness to label noise. So in these figures, noise has been added artificially to the data. These are different well-known benchmark data sets, and you can see very nice reductions in generalization or test error. And those are, if you're familiar with the machine learning literature, significantly high. You typically don't see that high reduction in test errors. Okay, of course, on this, and this shows sparsity here again. This is a higher level of sparsity. And I should probably conclude with saying we just ran extensive, very well instrumented tests on the D-Wave hardware to run the non-convex training objective. And we just got results back this weekend, but they are just too fresh. So we felt it was not prudent to share those yet. There might just be a bug in there. So it's a little bit too early, maybe bad timing. But we have it all set up so that with the new non-convex loss, we can run it on the D-Wave hardware, and we will report on the results. I'm out of time. I wanted to explain a little bit about the challenges we had mapping to the D-Wave hardware, and I also wanted to point out an unexplored opportunity, but yeah, I'm out of time, so I will stop here. Thank you.
Any questions for Hartmut?
Okay.
If you want to use the remaining few minutes to say some more about the things you were going to say.
Yeah, maybe rather than going through the, I should maybe point this idea out, or a thought that's pretty natural when you work with the hardware, is that the native mode of using the D-Wave chip is really not necessarily to use it as an optimizer that gives you the one best solution. It is often as valuable to get a portfolio of various low-lying solutions. So if you can sample from the various local minima, that is often as valuable, if not more valuable, than just finding the global minimum. Actually, there are whole fields in machine learning that all they need to do as a resource is sample from a probability distribution. And of course, since the D-Wave system doesn't work at 0 temperature, but at a finite temperature, the energy function defines a Boltzmann distribution. So if you set it up properly, then rather you have to, in any case, when you run the D-Wave hardware, you don't just run it once, you run it, let's say, 64 times, 128 times, and then you look for the lowest objective value. But rather than being sad that, oh, I had to run it 64 times, 100 times, and throw away all the other samples but the best, it is often very valuable to use those other samples that you have obtained, and for example, in a machine learning setting, give it to your validation stage, because often those obtain interesting solutions as well. In particular, if you keep in mind that our objective functions are not necessarily cast in stone, they come from data that can be noisy. So you always have to think rather of a family of objective functions that are in themselves a bit noisy. So using the hardware as a sampling engine, I think that is an interesting direction to look into going forward, and has excited already quite a number of experts in sampling methods for machine learning to look at the D-Wave architecture from that angle. So that was an idea I still wanted to share. Okay, you guys are all tired. That was the last talk.
If you would thank all the speakers, thanks for.
So I think we'll just go straight to our final session, which is